Okay, we talked about the graphs of sine x and cos x, and they look like this, like that. That was the sine theta curve. That's theta along there, and the cosine looked like that. Not very good diagrams. Cos theta. And we talk about tan theta in this screencast, which equals sine theta divided by cos theta. Or if we go back to the sides, if we just draw it in standard form like this, there's your right angle, that's theta, opposite hypotenuse adjacent, tan theta equals opposite over adjacent. It should be obvious to you that if we've got sine theta divided by cos theta, if cos theta equals 0, that means problem, because you cannot divide by 0. So what we're going to do is investigate what happens near points where cos theta equals 0. And we know from one of the screencasts at least, that cos 90 degrees equals 0 exactly. So what we're going to do, so tan 90 doesn't exist. And what we're going to do is look at this, and then I'll show you graphically what happens. So I'm going to look at the tan of 89 degrees, and I'm also going to look at the tan of 91 degrees and see what that looks like. Now, notionally at least, I won't be able to draw it perfectly, but we've got a very tall, thin triangle, and it should really go really, really high, and that's 89 degrees. Of course, it's not exact. So what have we got here? That's the opposite, that's the adjacent, that's the hypotenuse. And so what that's telling me here is that tan of 89 degrees is going to be the opposite over the adjacent, which is something big, because we've had to stretch this triangle really high, over something small. So that's a big number. So tan 89 is large. What about tan 91? Well, let's have a look at that. You'll remember the quadrant analysis which we did when we go back here. There's your hypotenuse, that's the angle we've got there. That's a right angle, opposite, adjacent. Now, the opposite is greater than 0. The opposite is greater than 0. The adjacent is less than 0 because we've gone backwards. So if we look at tan 91 degrees, we've got the same configuration, or it's the same shape of triangle as we've got here, but it's gone the other way. We've got to flip it over. So it's like this. It's a tall triangle, but going backwards. So there's my 91 degrees. This is the hypotenuse, always positive. There's the opposite, which is always, well, it's positive here because it's going above the axis. It's in the positive region. But the adjacent is negative. So tan 91 equals opposite over adjacent, which equals big over small negative. So it's something like 10 over minus 0.1, which equals minus 100. Okay, because a positive divided by a negative is a negative. So we've got tan. Well, let's work it out exactly. If I go back to my trusty calculator here, let's work out tan 89. Well, not exactly, but as near as this thing can do it. Where's tan? Here it is. Tan 89 is 57. I said it was big. So tan 89 degrees equals plus 57 point something, which I can't remember. Where are we? 289. Call it 57.3. Now let's have a look at tan of 91 degrees. It should be obvious to you from geometric considerations, because this triangle here is just a mirror image of this triangle here. So it's going to be minus 57.3, because all that's changed is we've taken a mirror image, and so the opposite is still the same, but the adjacent, instead of going this way, is going backwards because the triangle's gone past the first quadrant there. That's the right angle in there. So minus 53. Let's see if the calculator agrees. 91 tan minus 57 plus these other decimal places here, which I can't be bothered to write down. So that's equal to minus, I forgot the sign there, minus 57.3. Okay, well, that's quite odd, because as we approach 90 degrees, we're going to have something very peculiar. And of course, this effect gets stronger. If I look at the tangent of, let's say, 89.5 degrees, you see we're approaching that 90 degree. Let's work out the tangent of 89.5. Here we go. 89.5, take the tan, that's 114.6. 114.6. Some of you will notice that it's about twice that. What about tan of 90.5 degrees? Well, we know from geometric or by symmetry it's going to be minus 114.6, but it's always as well to check with the old calculator. 90.5 tan. Tan, there it is, minus 114.6. So something very peculiar is going on near this 90 degrees, because just below it we've got a large positive, and just a teeny tiny bit above it we've got a large negative. So what does it look like when we plot it? Well, it's not altogether obvious at all, and in fact, yeah, it's a bit of a shock really. Well, I've got one here that I spent quite a long time incidentally preparing. Here it is, and I'll take you through it. This is the tan function here. So this axis here looks at my axis in degrees. You see we've got positive and negative, so it can go around clockwise or anti-clockwise. And this green curve shows the tangent. And look what happens when we get closer to 90. The curve gets bigger. It's called an asymptote. I've had to cut it off at some point too, because if I didn't cut it off, this line will go infinitely high. And then at exactly 90 degrees, it comes whipping down here, and then it goes back up the other side. So we've got this nice behavior here on either side of 90 degrees. It gets bigger, and on this side it zooms down, and we've got negative. So it's plus infinity here and negative infinity here. We've got a discontinuity at these points here, simply because the triangle is so tall that at 90 degrees it doesn't even close itself at all. But very close to 90 degrees, we can see that we've got a very tall, thin triangle, which is very, very difficult to draw. So we know that tan, you write it, tan 90 degrees equals infinity. It's a bit naughty to write it like that, because, well, it's naughty for reasons that you'll find out from the next screencast. Okay, or the analysis screencast anyway. Right, I'm going to stop there.